This morning we are going to see this concept of the body plot. What is a body plot? And it's also called the frequency response plot. So let's go take a look at a simple example that would allow us to understand this. Let's just propose a simple circuit, all right, that we're going to call our system. And the simple circuit is something like this. We have used this example in the past for other concepts, and I would like to try it simple like this. So in here you have a voltage source, you have a resistor, you have a capacitor, and you have an inductor over here with value. Usually we use the letter L for the value of this. You have the current that circulates through this loop. We're going to call it I. So if we say that, as we have done in the past, the output is equal to the voltage across the capacitor, which is the voltage across the capacitor is 1 over C times the integral of I dt. Or if we do it in terms of the charge, this would be 1 over C times Q. What is your input over here? Is your voltage V. So what is the concept of the transfer function in this case? Transfer function, let's just put it like this. Is the relationship, so this transfer function, normally we call it g of x, is equal to the output that we want in relationship to the input. Yeah? So the output that we want is this one. The input is V, but we don't have the equations of motion of the system to be able to obtain the transfer function. So you can say that V is equal to I times R plus 1 over C, the integral of I dt, plus L or I, this is coefficient L times di dt. Or you could write, if I is dq dt, it follows that dq dt times R, that's 1 over C times Q. Times Q, and then the plus L times d squared Q dt squared. Well, we be using Q capitals, right? So let's just be consistent about it. Maybe do this little correction here. And then we go over here, then it's 1 over C times Q, and this is like this. Yeah? So if you apply the Laplace transform to this, what do you have? B of t in this case, like this. So you have S times SR times Q of S. plus 1 over c times q of s plus s squared, s squared times q of s, yeah, times L is equal to voltage of S. Remember, the output is the in here. If we look in more detail and factor in this, you could have that S squared times L plus plus 1 over C plus SR, this like Q of S. So one relationship between the output and the input, isn't it true that this is the input V of S multiplied by, what is this, the plus S squared times L plus S times R plus 1 over C. Q divided by this is, you see, there's a slight mistake in here. So it's 1 over, not like this. It is over here like this. So this is 1 over S squared times L plus S times R. So this is the expression that we have for the, let's see if we can use the space on the right hand side here. What is the voltage of C in this case? Voltage of C is, as it's in here, actually up there. The voltage of C is 1 over C times Q. Yeah. So voltage of C, voltage C of S, voltage C of S is equal to 1 over, okay, so this is, if we have Q over here, it follows that Q of S that B of C, really voltage is 1 over C times B of S, and then multiply by 1 for S square R plus R times R plus 1. So this is the output frequency. If we want this result. So the transfer function in question is this. This is your system. Isn't it true that if I make, let's say I decide to make the the analysis without using much of the remaining C element, but just this, we have this equation says voltage of C is 1 over C times this. This is the transfer function. So in here, I could say that you have, this is your system. In fact, let's just draw it here for consistency, that this is this is your input, and this output okay. So this is the transfer function, is 1 over is R squared then it's correct. So what I'm trying to say, and in introducing the body concept, is we have this transfer function right now, and what we are trying to say is that the system that you see in there can be tested, okay? Like in here, this is your system. So if I put something here, I should get something out of here. So what happens if I, let's say if I put a signal like this? What will happen on this side? Yeah. So this is the, right. So this is the input. The output should actually track the input. It should be like this, all even. So the answer also will have a sinusoidal input. However, not necessarily the same frequency would be in the answer, so they could be out of phase. In other words, what we're doing is we're coming in here with this transfer function and putting a sinusoidal input to it, and after that we need to make a plot on as to how this would plot. See, one thing I want to say before I do that is whatever the phase is in here not necessarily be the same here, either ahead or behind, because the curve will move if we test it like this. So in this case, you have a really body plots are two plots in one. Let's say in this case you have this is of course is time, and this is any variable x, y, or z. Let's just say y. Y is your output. So if you put the one signal here, it might look like this. But if you put the other signal there, I'm going to change color so that you can see it. Y and T. What I'm trying to show you is that if this is the input, the output may not necessarily be in phase. Maybe the output is out of phase a little. Okay, so the response may not be exactly like it. It will be again a sinusoidal, like this. The difference between these two is called the phase phi. So our objective is entering a transfer function in KMG produce this plot. So if we could do that for the system, I think would be really nice. In fact, let's just go to MATLAB and try to do it. I think that would be the best. I'm just gonna keep this other one on the side so that we can look at the format of this equation. And then enter it in MATLAB. You enter the transfer function, like here we say like the numerator is equal to 1 and the denominator is equal to whatever coefficients we want to give it, like a 2 and a 1 and a 1, like this. And you have the transfer function to be g is equal to num then tf of numerator and the denominator, yeah. And so I get the transfer function here, and I could do this. Body G, get me that body plot that tests the frequencies from very low frequencies to very high frequencies and see what the system responds. That's why this method is called frequency response. And there it is. We have the magnitude plot on the top, and this is the phase magnitude on the bottom. So this will show how close the input tracks how close the output tracks the input. But I think that's enough for now, just for the basic concept.